Hello everyone, I'm Zhang Zhao from Shanghai Jiao Tong University, and today I'm excited to present our work on grounding and enhancing grid-based models for neural fields. This is a collaborative work with Dr. Feng Fan from the Chinese University of Hong Kong, Dr. Wenlong Liao from SJTU and Kua Technology Limited, and Dr. Jun Qian from SJTU. First, I'd like to introduce the neural fields and their broad applications. Neural fields are coordinate-based networks that represent a field, essentially a continuous parameterization that represents a physical quantity of an object or thing. Neural fields have shown significant success in various tasks in computer vision and in other research domains. We target grid-based models, which are a major series of models for neural fields. Grid-based models are fundamentally different from conventional neural networks such as MLPs in their parameterization and function. As shown in this diagram, a grid-based model takes a query coordinate as input, which is sent to an index function to acquire a set of feature vectors from the grid. The model then outputs a weighted average of the kernel function and these feature vectors. We aim to understand and enhance grid-based models through three main questions. First, how can we understand the training dynamics of a grid-based model? Second, how can we measure the generalization performance of a grid-based model? Third, how can we design a better grid-based model? To address these questions, we propose a theoretical framework based on tangent kernels. Our theoretical results show that the approximation and the generalization performance of grid-based models are related to grid tangent kernel. The GTK is defined as a positive semi-definite matrix that measures the difference between two data points in the gradient space. Here we show the definition of the GTK. G is a grid-based model parameterized by WT. X is a dataset where Xi is the S data. We will show the derivation of the GTK in the following slide. The model parameters evolve according to a differential equation. The gradient flow is described in equation 3. By substituting equation 3 into equation 2, we derive that the GTK is related to the training dynamics of the model. Here is the first theorem we introduced. Informally, theorem 1 states that when optimized by gradient descent, the outputs of grid-based models evolve following an ordinate differential equation related to the GTK. Formally, the evolution of the model outputs is governed by equation 5. After that, we propose another theorem. The theorem 2 states that the GTK of a grid-based model stays constant during training. This means that the initial GTK remains constant throughout the training process, regardless of the grid-based model's status. This slide shows theorem 3, which can depict the generalization performance of a grid-based model. This theorem reveals that the generalization performance of a grid-based model is determined by a specific metric delta. Formally, this generalization bound provides a probabilistic assurance of the model's performance, indicating that the bound tightens with increasing data. You can find proofs of these theorems in our supplementary. Our GTK theories can inspire future designs of grid-based models with better training and generalization performances. We further introduced a new grid-based model named MorphaGrid. This model uses Fourier features to boost the learning of high-frequency signals and adopts multiplicative filters to inform the model with node information. We then present a set of numerical experiments based on the GTK theory. First, in the spectrum analysis, MorphaGrid shows a wide spectrum, especially in the high-frequency domain. This characteristic leads to faster convergence for high-frequency components. In the next experiment, we constructed a dataset with two data points and their corresponding labels. MorphaGrid demonstrates a tighter generalization bound for most values of the labels, indicating better performance. This slide shows the error maps of various baseline methods and ours. The error maps measure the difference of the predicted images compared to the ground truth. MorphaGrid provides a more accurate fitting, demonstrating its superior performance. Here we showcase the performance of our model in fitting 2D images and 3D sign distance functions. The results highlight the accuracy and efficiency of MorphaGrid. Finally, we present our results on novel real synthesis. The detailed results indicate that the MorphaGrid excels in generating high-quality novel views. underscoring its practical applicability. Here are a set of references. Thank you for your attention.